Yeah, so let's get started. Everyone, thanks for joining. Thank you for hosting us. The team at Elephant Scale has so graciously offered to feature a talk in Apache Druid today, and we're super excited to be here. I am not a technical evangelist, but good news, Sergio Ferragut is, and he's going to be speaking to all of you today about the goodness that is Apache Druid. Sergio is a senior, right? You're a senior developer advocate
Yeah, I'm
at
old.
Implied. And that just means he has a lot of experience, not that you're old. And he has, I believe it was 16 years of experience before this at Teradata. Is that correct?
Yeah, and other things, but yes.
And other things as well. And now he's been at Imply for not quite a year. In that time, he's done a lot. If you Google his name in Apache Druid, you're going to find a great plethora of talks that he's done all across the world. Most recently, he was in Sydney and Melbourne, Australia, speaking to the Melbourne Data Engineering Group. He also spoke at the Sydney Apache Kafka Group, and he participated as a mentor in a hackathon, which I'm excited to hear more about. He's also going to be speaking at some pretty big industry conferences in Berlin and Amsterdam coming up. And he also helps lead training and education efforts around Apache Druid and Imply. So I'll let you take it from here. Thank you so much for being with us today, Sergio.
Given all that introduction, I will not introduce myself, but let me share the screen. You should be seeing the presentation now. All good? I'm going to assume
yes.
That's a yes. All right. Well, thank you. Like Yana said, I'm a developer advocate, Sergio Ferragut. I work for Imply, but my job is about the open source Apache Druid project. So today we're going to talk about the rise of immediate intelligence and the Apache Druid database and the project and how it drives modern analytics applications. So so what we're going to talk about is the data temperature spectrum. This is the idea of hot and cold data and hot and cold analytics. Then we'll talk about how the databases over time have evolved to address analytics and what's the current and how we got to the current landscape and where Druid fits in that landscape. We'll talk about Druid's own origin story. And why it came about and, what kind of use cases it solves. And then we'll dig in, we'll open the hood and show a little bit about why it delivers on everything we're saying. And I'll leave you at the end with a few more resources to learn more about Druid and to begin participating in the Druid project. So with that, let's start with the temperature spectrum. So we're trying to create a contrast here between hot and cold stuff, right? And particularly when it comes to analytics. And we're drawing, a black and white contrast here. There are obviously shades of gray in between these, but we're trying to distinguish traditional BI from what we're calling immediate intelligence. And so in the traditional BI world, it's a colder experience, right? The queries, data isn't streaming, right? It's not real-time data. It's typically batched on a daily basis in the best cases. Sometimes it's weekly or more. So the data cadence and how fresh it is not isn't immediate. There's also this group or the people who exercise this kind of analytics are typically data analysts. They understand the data models, they understand the data structures, they write SQL, and typically they're asked to answer business questions, and they know, because they know the data structures and the sources, they can figure out how to build the appropriate SQL or the appropriate data access patterns to produce the answers to those questions. But that process, the process of building those analytics or the process of producing those results isn't an incredibly fast process, right? It may take minutes to hours. The queries themselves, because of that cadence, the queries themselves, it's okay for them to be a few minutes or maybe a few seconds. The experience isn't a fast interactive experience. It's a low concurrency situation, mostly for reporting or some ad hoc questions. But that's the landscape of BI that we're trying to describe here. On the other hand, the hot data or the hot analytics experience is very different from that perspective, right? It's critical that the data be available immediately, right? You have event data from the last few seconds that you want to be able to analyze as those events are occurring. The decisions around this have immediacy. The application, the idea of this kind of application is to provide informed decisions based on not just the history of the data, but based on what's happening right now. So in order to take immediate action or just go do more research, right? Sometimes it's about asking the next question. So these apps democratize data. The end users have immediate access to the data. That's the intent of this kind of application. Once they're in place, people socialize the data more, right? Because they have this ability to interact with the data quickly, they tend to communicate it to other people and communicate, the kinds of insights that they're seeing, and so more that tends to create growth in that user base, and therefore create higher concurrency. Because the queries respond with sub-second response times in this kind of environment, it creates an interactive experience with the data, right? It is about interacting with it immediately, seeing results immediately, and asking the next question immediately and seeing the next results immediately. So it's about checking theories, it's about validating and understanding and achieving insight very quickly. So just to summarize the contrast we're creating here between business intelligence and immediate intelligence is we're focusing on speed, we're focusing on the democratization of data and socialization of the data, the ability to do exploration of the data, this idea of personalized decision-making instead of strategic decision-making. And it's not just about access to the latest data. So it's not just the streaming data and trying to understand what's happening right now, but understand it in the context of historic data and be able to do comparisons as an example. So what are the use cases? In risk and fraud, we see fast-moving transactions, right? Like credit card transactions is a good example, right? And there has to be some deep analytics associated to them, things like individual spending profiles or recent spending profiles for the cardholder that's producing the transactions, and understanding the current transactions in the context of those past profiles in order to evaluate fraud or not fraud possibilities of a particular transaction. So this needs quick analytic responses. It's typically machines generating high concurrency of queries because as credit card transactions are occurring, they need to be evaluated. So it's this kind of use case, large volumes of transactions, large volumes of historic data that need quick analysis and quick response. Another use case is the data-driven applications. These are websites or mobile apps, right, that have some kind of analytic component. In successful websites and successful mobile apps, the concurrency is off the charts. We're talking hundreds of thousands or millions of users that are potentially issuing queries and need that kind of response time. So, and many of these applications are consumer or customer facing, right? And the reliability and speed of the underlying database translates directly into what the customer experience is in this application space. In network performance, it's all about service reliability and security, right? There's definitely a need for fresh data, and there's tons of data. We're talking about packets of data in the network and understanding what their path is through the network, right? Understanding at the higher levels traffic patterns and how those are changing, and whether some traffic patterns are potentially an attack and therefore need some action in terms of security, or there's some kind of failure in the infrastructure and that needs attention to address reliability. In clickstream analysis, it's about understanding journeys, right? It's about understanding what users are doing and what they've done first, what they clicked on next, what they clicked on after that, and understanding that in the context of many users and how different users interact with the user experience that the application is delivering, and understanding the now, what the user is doing now, and based on that, providing a personalized experience for those users. So again, there's large volumes of data. Clicks are huge, especially in big websites. So it's about again, understanding the context, understanding the what is happening right now, and taking action based on the analysis of that data. And I won't go through all of them, but another one that's interesting is digital ads. It's particularly interesting because that's where Druid was born, in the digital advertising space, where it's about impressions and click-throughs, right? It's about segmentation and targeting goals. So quick analytics on live campaigns are very useful in order to adjust campaigns and retarget them and make them more efficient, get more bang for your buck in terms of from the advertiser's perspective, and therefore increase your click-through rate. So again, lots of data, lots of concurrency. And that's the common theme here. So let's, now that we understand, the difference between hot and cold data, let's walk through how the database world has evolved to deliver on this idea of analytics over the last, I guess, 30 years or so. So we started here, right? We started with the relational database. Well, some started before that, but let's start there. The relational database was first used to implement transactional systems, right? The idea was to operate the business. So we started recording business transactions like sales orders and shipping orders and inventory and purchase orders and so forth, right? And by recording all of that data, it became available for analysis. So into those applications that we were building back in the 90s, we started in things like Informix, Oracle, or SQL Server. We started also adding reporting capabilities to these applications, right? So we added some queries that would generate reports, and those queries, particularly the ones that spanned more time, started consuming a lot of resources. So there was this competition between the analytics of the business and the operation of the business. Obviously, from a business perspective, operating the business became more important. So the architects at the time decided we need to separate the workload because analytics of the business are also important, but we can't stop the operation of the business in order to do the analytics. So the idea of the data warehouse came along, where we take transactional data from the transactional systems, from the operational systems, and move it out into a data warehouse. Data warehouses, technologies, there's a bunch of them. Netezza, Teradata, Oracle did it as well, SQL Server, Greenplum, and there are many more names, right? But these technologies were mostly scalable technologies that allowed you to do parallel query processing and therefore enable this analytics at a somewhat larger scale. Part of the problem here now is that a new problem appeared. Or a new set of pipelines appeared called ETL, right? Extracting the data from the source systems, transforming it, and loading it into the data warehouse. And this typically involved having a defined schema on the data warehouse, a very well-defined schema that described the business well, and transforming the data from the source systems to conform to that description of the business. That process, took time, right? It took time spent on data source analysis, business process understanding, profiling, cleansing the data, delivering a highly structured data model designed for the reporting that was needed, and you data model to make it usable within the cost constraints of whatever the technology you had, right? So this, in some cases, involved some aggregation. In some cases, it didn't. It involved larger scale databases. But the whole process of building data warehouses took years, right? And increasing the availability of more data in the data warehouse also took time. So that created a somewhat colder experience. Even though you could answer now questions about anything in the business, and we weren't bugging the operation anymore, it still didn't provide a hot experience. So the first thing that or one of the things that happened was we started seeing OLAP databases appear as offshoots, as data marts, extracting data from the data warehouse, building specialized subsets of data that were aggregated in some form. And we also provided some kind of visualization tools to allow the end users to create their own visualizations and to do their own reporting. This increased the temperature, right? From an end user's perspective, it allowed them to define new reports, at least on subsets of the data, without having to go through the whole, month's worth of the request of the data warehouse people and the building of new reports. So it enabled this ability of end users to self-serve and that increased the temperature as well. Now, the data continues to accumulate, and there's still some lag between the data, the events occurring, going to the data warehouse and building OLAP data marts. But this was a successful approach, and we started seeing an appearance of many data marts. There was the sales data mart, the marketing data mart, distribution data mart, all for specific purpose analytics. And some of them were even, rogue, where they didn't want to wait the time it took for the data warehouse people to get the new data. So they just went directly to the source, and those became somewhat of an IT nightmare. But anyway, this was the landscape when we saw big data start to occur, right? This mid-2000s, we started seeing sharding of databases, right? The transactional databases, the OLTP system started separating the data by something, it could be by customer, by region, by store, whatever made sense to split up the workload, because transactions, the operations of the business were also getting bigger, and the single database instance wasn't cutting it anymore. So we started sharding the data, separating the workload. Distributed computing ended up helping the operational burden side. With that also came this idea of the data lake. The data lake's main difference to the data warehouse was that instead of trying to conform the data, like in the data warehouse where you're building a specific model that describes a business, you would just take the source data and store it in the data lake as is, right? And then allow distributed query engines. And this is where another component appears, this ability to do scalable queries on the data lake data. Now, part of the issue here is that the ETL didn't disappear. ETL still exists, but now it was transferred over to the data analysts that use these query engines and that understand all of the different sources of data and could therefore take advantage of them. And they did, right? This is a good solution to do general purpose analytics, but it's still not a hot experience, right? We've solved the problem of scale, both on the operational side, we've solved it on the analytics side, but the process of creating and accessing that data still provides somewhat slower queries. We're talking multiple seconds, even minutes, to produce results through this mechanism. So to top it off, we had more sources of data appear, right? Like the websites and IoT, and now we have streaming technologies like Spark, Kinesis. We have streaming transformation technologies like Spark and Flink. And I said Spark before, I meant Kafka. But anyways, Kafka, Kinesis as streaming engines, and Spark and Flink as transformation engines on the stream. So real-time data moving and being transformed, but being placed into the data lake, and then have some query engine that wasn't really able to address that real-time stream and be able to analyze it as it occurred. So the need for something that's called a serving database appeared, right? This is the idea of let's create an optimized version, subset of the data. So it's similar to the data mart strategy of the early 2000s, in that we're now taking a subset of the data that's particularly interesting for analytics in a faster interactive experience, and producing some optimized form of that data so that we could access it quickly for application purposes. So early implementations of this were done in Cassandra or HBase with key value stores that were highly scalable, but it required that you build the analytics ahead of time. Now, this is the space where Druid fits, right? Druid is a serving database for fast analytics. So it has an optimized copy. But Druid is a little different than those early implementations because it's meant to resolve a few things, right? Very high concurrency, low latency queries, high data volumes, and lots of flexibility in the kinds of queries. It was different than a key value store in that perspective because it's not, it doesn't have pre-resolved queries. What it has is a column-oriented data format with compression, same kind of columnar stories that we saw in the data marts in the OLAP space a few years before. But these are with ORC or Parquet files in most cases. In the case of Druid, it's not those standard formats. It has its own format because it uses indexing of all of the dimensions. And so as it builds these data files, they're all indexed. It allows for streaming ingestion and batch ingestion from data lakes. And it has a resource management that provides efficiency across a cluster of data. So what this means in your architecture, right? This fits, this particular database fits the use case of immediate and hot analytics, right? You don't necessarily want all of your data to be in this form, so you wouldn't want to put all of your data lake into this form because that's going to be expensive, right? This is meant to drive analytic applications that need that real-time experience and that need that interactivity. So it fits this particular space within the data environment. Now, Druid also enables not just the batch data from the data lake, but also the streaming data, right? So it can read the data directly from a stream or directly from a transformed stream coming from Flink or Spark, such that the real-time data, the events from the moment they occur to the moment that they're analyzable are almost instantaneous. It depends on what you're doing in the pipeline, whether it's instantaneous or not, but it's within seconds that an event of data is available for querying within Druid. So with that, that's sort of the whole history of the database evolution and where Druid fits in that picture. Let's go a little bit more into how Druid came about and how the open source project came about. So back in 2012, 10 years ago, there's a company working with advertisers and publishers in this highly competitive ad tech space. So like I said before, Druid was born in the ad tech space. The idea is if you can prove to the advertisers that you can offer the best publishers and the best locations for their ads, there's money to be made in that, right? So it's really about providing analytics to the advertisers so that they can see how each of those market segments behaves within the advertising spaces that there are. Now, this new company wanted to do something new, right? It wasn't just about providing analytics like many others were providing, but they wanted to provide real-time analytics because this was a competitive space and they saw that as a competitive advantage. So what they wanted to deliver was an experience like this, right? These videos show a user, well, in 3 different cases, a user dragging and dropping dimensions, changing filters, drilling into a particular part of the timeline, and the response time that you see is not accelerated at all. So this is the response time that you expect from what we're calling immediate intelligence, right? It's that interactive experience where you can ask one question and the next question is a click away, and just less than a second away, you get results, right? So it's about having this conversation with the data. So because they wanted to build this, right, they tried almost everything that we went through in the history of the databases, right? There's this group of engineers in this company tried relational databases, tried data lakes, data warehouses, search engines, time series databases, and they found that all of them presented some or another problem, right? In some cases, it wasn't scalable. In other cases, disjointed. The stream data versus the historical data weren't directly queryable together. So this and the response time wasn't at the level that they wanted to in order to create that interactive experience. So instead of using available technologies, they decided to create new one, and they created Apache Druid. They set out the requirements for it. They said it had to be high performance. So this meant low latency, distributed query execution for scalability, and high throughput ingestion from streaming engines and from batch sources like S3. It had to be real time, so event data had to be able to be analyzed within seconds, and had to provide a broad set of analytics like counting, ranking, statistics in general around any kind of combinations of dimensions of the data. And it had to be a database, right? It had to be highly available. It needed to be time sharded in order to provide distribution of the data across time. It had to be a columnar in order to provide analytics across multiple dimensions. It had to be pre-indexed to enable that fast execution, compressed, also helping the fast execution with the ability to do late materialization. So those were the requirements, and they started building it, taking learnings from all those other databases that they tried, right? So from log search engines, they took the real-time ingest capability and flexible schema and text search capability. From time series databases, the low latency ingest, this is from the time of the event occurring to the time of it being stored in a way that's analyzable, would be a really short time frame, and a series of time functions that allowed you to play with different time granularities when doing the queries. And finally, from columnar databases, the columnar structure itself, which is an efficient storage for analytics, to provide fast analytic queries and provide data distribution in a cluster that enabled parallel execution of the queries. So with all those ideas, they built Apache Druid, and it works, right? It's something that can provide ingestion to the scale of many millions of events per second, and this is a proven thing. The query engine gives aggregate results with sub-second speeds, and the storage system is storage and compute efficient, so it can give a unified view of both historical and real-time queries. So they succeeded. They built this application. This company was successful, and it was ultimately acquired by some other company. But what they did when they were building this is they open sourced the database technology that they built for it, and that's Apache Druid. You can read the paper if you're very technically inclined. It's very interesting in terms of the overall problem definition and how they came and what the architecture was to solve that problem. Once they open sourced it, it didn't take long before Netflix adopted, and they were one of the first adopters and started also contributing to the project because they adopted it because they had the same kind of problems in terms of scale, right? In terms of data volumes, in terms of high concurrency, and the need for very quick response times in the queries. Along with them came others, other big names in big data, or other companies that have large volumes of data and large concurrency, like eBay, Yahoo, PayPal, and Cisco. And these became the PMC for the Apache Druid project, the first project committee. With that, many more came, right? There's many companies out there using Apache Druid for any number of different use cases, like video streaming analytics, infrastructure monitoring, clickstream analytics, API health and monitoring and reporting, all backed by this developer community that is the Apache Druid project. So unless there are any questions there, now I'm going to dig a little deeper into how it works. So a little bit into the architecture and the file structure and how that allows fast query response times. No questions, I'll move on. All right. So again, this is the landscape, right? And Druid fits as a delivery database with this optimized form of the data. The architecture looks like this. So if we start from the idea of ingestion, data ingestion, we have on the right batch data or streaming data. And both batch data and streaming data are the process of ingesting, whether batch or streaming, is completely scalable because it's in the data servers, the indexer processes that can be scaled to any level. and therefore provide ingestion throughput at almost any level. There are limitations on the streaming side. You're limited in the parallelism from the number of partitions in the Kafka topic, as an example. So that's the maximum number of tasks that will be able to be streaming at the same time, but it's configurable both on the Kafka side and on the Druid side, right? In terms of how many partitions exist in a particular topic and how many indexers and how many workers those indexers have to read from those partitions in parallel. So it's a scalable ingestion process, both in the streaming and batch data cases. So as the indexers ingest streaming data, they have the data in memory and make it available for querying. So that's how the real-time component is solved for the query side, but we'll get back to the query side in a second. The indexers are ingesting the data, whether streaming or batch, and they produce, you see these yellow squares all over the place with the gray columns on them. Those are the segment files, the columnar structure we're talking about. So the indexers are in charge of ingesting and creating these files and then putting them in deep storage. Once they're put in deep storage, they're persistent, right? Deep storage can be used, it can be S3, HDFS, any distributed file system that provides reliability for the data. So once it's there, the coordinator knows of new segments being published, and it distributes segments across historical. So we go back to the data servers. So the historicals load the segments of file that they're assigned. There are replicas of a segment file in multiple historicals to provide high availability. But these historicals now have a cached copy of the segments, a few segments that they're in charge of, that they can respond to queries with. So if we go back up to the query server, queries come in through the query server, whether in SQL form or in the native JSON form that Druid uses. And the broker knows where the data is. It knows, how the data is time sharded, which historicals have which portions of the data, which portions of the data are still in memory in the indexers because they're being streamed in real time. And therefore, it can, based on the query, based on the time intervals that the query is looking for, it can figure out very quickly which historicals it needs to talk to and which indexers it needs to talk to in order to resolve a particular query. So it creates individual requests. It fans out these requests to the data servers, to the corresponding historicals and indexers that are needed to respond to a particular query. They do the analysis on either the segment files or the in-memory data that they have, and produce subsets of results, which are then sent back to the broker to do final calculus or final group bys, final merges that are then returned back to the user. So that's sort of how it works at a high level from an ingestion and a query perspective. One other thing to note is that the master servers are in charge of coordinating the cluster, right? And what the coordinator is primarily doing is looking at all of the segments that are available, so in deep storage, and continuously deciding where they belong, right? Which historicals should have a copy of them. So as the cluster is scaled up or down, so if you add more historicals, they will very quickly make new decisions about the segment distribution and ask historicals to either unload or load segments to redistribute the data accordingly. So it's easy to scale up or down historicals because the coordinator is automatically doing this distribution job. And providing high availability along the way because it has rules per table. You can define how many replicas you want, which enables parallel execution of the same analysis of the same segments, but also enables high availability. If you lose a historical, there's another historical with a copy of the data to respond to the queries. So with that, let me dig into what the structure of the file actually is. So the structure of the segment files use 4 different strategies for their efficiency, right? They use compression. This is the values of all columns are stored in an encoded form. That means that we store an index to a value rather than the value itself. So that's typically a smaller piece of data than the original value. The original values are stored in a dictionary where all the distinct values are kept, and it's kept in sorted form, and we'll see why that's important. But that by itself compresses the data, right? And then the use of repetitive values, there's an additional compression, algorithmic compression used to compress these files. So they're stored in a very efficient way. All dimensions also get indexed, and we'll talk a little bit more about the structure of the indexes in the next slide, but it's automatic, right? You don't need to define indexes in Druid. It's any data ingestion, all dimensions will be automatically indexed. And finally, the use of late materialization. This is the idea that we're processing the queries with the encoded values throughout until the very last moment in which they need to be translated back to their original values using the dictionary. So this allows you to process the data in compressed form and only expand it to the original data values as needed, which makes it more efficient. So let's walk through an actual example. There's only 8 rows here, but normally each segment file has around 5 million rows. That's the recommendation. But you can control how big the segment files are based on the ingestion process. So each of these segment files always have a time column. You see __ time because it is a time-sharded database. So segments are split along the timeline. And within the segments, each row has a timestamp associated to it. Then there's the dimension columns. In this case, we have artist and city that are, like we said, encoded. The data is encoded. It's encoded based on the dictionary. The dictionary is a list of distinct values within that column, sorted and then encoded such that it's easily searchable because it's sorted. And then there's an index associated to each of those dictionaries such that the first entry in the dictionary corresponds to the first entry in the index, and so forth, right? The second one to the second one, and so forth. So if you look at the index on the artist column, you'll see that for the value ACDC, we have the first index representation is just a list of row IDs or row indexes within this segment. So we see that ACDC appears in rows 0, 1, and 2. And then there's a bitmap representation of that that shows a bit turned on if that value is present in that row, or turned off if the value is not present in that row. So each bit represents a row within the bitmap. Now, those become very useful when you're doing combined where clauses. So if I have artist equal to ACDC and city equal to Melbourne, we can use the value from each of the first entries of the index to very quickly do a bitmap operation, a bitwise operation on the two in the roaring bitmap indexes, such that the result of the AND operation gives us the resulting rows of the where clause. And the same can be done with ORs, ANDs, and complicated where clauses, right? So this becomes a very efficient way of operating on multiple columns and finding the rows that we need for a particular query. And finally, you have the measure columns, which are the data elements, right? In this case, we have price and count. So let's look at how a query would be resolved with this data structure, why it makes it fast. So in this example, we're looking to aggregate the total sales by artist ACDC by city. Right. So in order to solve this, the first thing that happens is we see where artist equals ACDC, go to the artist column structure, read the dictionary. And because it's sorted, it's a very quick search. Even if it wasn't the first value in the list, it's a very quick operation to find the value. And then based on the index of that value, so if it's the first element of the dictionary, we go to the first element of the index, and that tells us that we only need to look at rows 0, 1, and 2 in any of the other columns that are involved. So with that, we go to the other columns that are involved, which are in this particular query are city and price. and just retrieve the rows 0, 1, and 2, the ones that are relevant to this particular query. And then do the aggregation operation, right? We have 2 values for city equal to 2, 1 value for city equal to 1. We aggregate the price and produce the results still with the city encoded. Finally, we do the late materialization part, which is converting the dimensions to their original values. So we take the encoded values of 1 and 2 and translate them to Perth and city. Now, one of the things to note here is that we didn't have to scan the segment file, right? We didn't have to read the whole thing. If you have any form of where clause inside a SQL that you're doing, it'll definitely help in retrieving a lot less rows from each of the indexes. And it's a very quick operation to go look at individual elements within an array, right? Which is what the columns are here, to retrieve the values that are needed. So it's a very efficient way of resolving queries for each of the segments of data. Now, in a bigger query, this might involve multiple segments, and therefore we take advantage of the parallelism of the historicals and of the indexers to process a request in parallel and do that kind of processing for multiple segment files at the same time. So anyway, any questions there before I move on? All right, any in the chat? Oh, there are some things in the chat. Let me take a look. Well, actually, there's somebody telling you there's a typo in ELT, but in that case, it's actually an extract, a load, and then a transform that occurs at the end. That's why we did it that way. Any SPOFs, query server or master server, for example. I'm not sure what is it. What do you mean by an SPOF?
Hello.
Yes.
Yes, sorry. Hello, my name is Christian Schlichter. I have quite some questions. I'm not sure if this is the right time to ask,
Yeah,
or
this
is
is
there
the
a separate
perfect time.
Q&A session? Okay, so the single point of failures, I mean, so there is only, in this diagram, I see only one query server, one master server, but maybe they are scaled out?
No, there are actually multiple master servers and multiple query servers. So there is high availability in the coordinator process and in the broker process. In the coordinator process, there's always one leader, right? But typically they're deployed with 3 instances of the coordinator process, just like Zookeeper is at least 3 instances. And it uses Zookeeper to do quorum evaluation when there's leader election to be done, right? If one of the coordinator fails. So it does provide that high availability. There are no single points of failure in the architecture.
That's cool. You mentioned the data lake. In your diagram, there still is the data lake. Does Apache Druid replace this data lake in some circumstances, or would you still need one?
And I don't see it replacing the data lake, right? The Apache Druid is about delivering fast applications, right? So you're taking some subset of the data and putting it in a form that allows for this very quick analytics for a particular application purpose, right? Where a data lake is more about having all the data, right? It's about having all of the data from the sources available for different purposes. So even the distributed query engines that we were talking about, it definitely still have their place, right? It would be a very high cost to put all of the data into a Druid cluster to enable that kind of analytics across all possible data. I mean, we'd be glad to help you do that, but that's not really the normal use case. So data lake is still there, and you know, the query engines that are distributed query engines that access data lakes directly still have their use cases in the colder analytics.
Okay. What about the storage efficiency? So you mentioned compression and everything, but maybe you have some heuristics about storage efficiency. Let's say I want to ingest 1 GB of uncompressed CSV data. How much storage would it typically occupy in the deep storage that you mentioned?
It's going to depend, right? We actually have some formulas, where we, for example, in JSON data, we typically see a 9x reduction in the volume to the compression. From CSV, it's a little less because it's not as expressive as JSON. And it depends on the cardinality of the columns, because the dictionary, it's very different to store a dictionary of just two values, true and false, for example, versus a dictionary of, millions. If the columns are very unique, there's less compression, right? So it's hard to tell you exactly what the compression will be. It's going to depend significantly on the use case. But there are, our rule of thumb with JSON is about 9x.
Okay, that's good, because as a DevOps engineer, for example, if you want to set this up, you need to know these things. So because
Absolutely.
you know how much data you ingest, you need to know how big the deep storage needs to be. Okay, thank you. Next one. How does the system, because of all the compression and the indexing, how does it respond to bit rot in the storage? So what happens if a bit flips? Is all broken, to non-recovery, or is there a way it gracefully recovers?
That's a deeper question than I know how to understand, than I know how to answer. Sorry.
Yeah.
But
so what I mean.
It's an interesting question for sure, and it's something that I can take back to engineers that have deeper knowledge of this than I do. So I'll take that question back and hopefully respond to this group with an answer.
Okay, good. Thank you.
Thank you. So let me see, any other questions on the chat? The optimum size for data that can be considered for Druid. I'm not sure what you mean by that, but the Druid can be implemented in a single node in the smallest case, in which case you wouldn't have high availability, for example, all the way up to the biggest cluster that I know of is about 1,000 node cluster. We haven't seen a limit, right, to how big it can be. So I don't think there's an optimum size. It just enables from very small to very large implementations of this fast analytic capability. Hopefully I answered your question. Let's see, Patrick Liu, how do you compare with Trino and Dremio? I don't have a specific comparison to Trino. I know Dremio is sort of a different thing. Dremio is a federated query engine, right? It takes a query and distributes it among multiple databases, depending on on the metadata that it knows about what data is where, and then it processes the results of those and merges the results together. So from that perspective, it's a different engine. I don't think Dremio can deliver the fast analytics that because it's depending on other databases to actually execute the queries. It solves, I think, a different problem. Trino, I think, does solve a very similar problem to us, but I don't have a comparison for you. I'm sorry. I don't know what the result, what the speeds and feeds comparisons are. Okay, so I think those are all the questions. Let me see how we're doing on time. We've got about 10 minutes left. So with that, let me move on to a few other things. We've the community at large, both Implied customers and Apache Druid users on their own, have implemented Druid using multiple different front ends, right? We've seen implementations with Grafana, Looker, Tableau, Superset. There's also, and that's just the visualization tools that help you take the data and produce some visualization and take advantage of the speed of Druid to do it quickly. There's also custom applications that are developed with a Druid backing. So Druid enables connections either through JDBC or through REST APIs. That any of these application technologies can take advantage of, such as Elixir, .NET, React, and Angular. So we see those and many others in the community creating custom applications. And we also see it even in data science, right? We see both machine learning models being used in the data pipeline to enhance the data that is then available for quick analytics to end users. And we also see it used as a way of producing quick analytics to feed machine learning models in real time and produce results from there. So with that, I'll just point to a few more items to learn about here. There's, if you go to the Apache Druid powered by page, so this is in the druid.apache.org website. If you go to the powered by page, you'll see many use cases, right? There's hundreds of use cases here of Druid users that have implemented Druid for different things, and you can learn about them. And many have links to videos. There's Druid Summit videos that people have created, like Netflix describes their whole environment in the last Druid Summit. So if you go to druidsummit.org, you'll find a bunch of videos there as well. There's the Druid Forum. This is druidforum.org, where we participate and the community at large participates to create articles about use cases, about implementation details. It's a Q&A forum where people ask questions and do troubleshooting. So the community is helping the community here be successful with Druid. There's the Apache Druid website itself, where you can download the Apache Druid software, try it out for yourself. There's lots of documentation there with tutorials about how to implement it, both in small standalone way or in clustered form to test out Druid yourself and to do implementations yourself. There's the GitHub project, which is the heart of the open source project, where we hope to gain more and more people. It's been starred over 11,000 times, and there's over 3,000 forks. So it's a very active project. And we're always looking for more people that want to participate, and not just necessarily in coding, right, and in building new functionality, but also in helping us refine the documentation. Maybe the documentation isn't clear about something somewhere, and people can submit the changes to the documentation. And so all of those PR requests are reviewed by the community and implemented by the community through this project. Obviously, if you code, if you understand distributed systems, and you like to get into that level of detail, we're always looking for more people to get involved in evolving Druid to new features and new capabilities. There's our own website, Implied's website, where we have different blogs, our own company blogs, engineering blogs from the engineering team that's part of building Druid, and community blogs from the community at large about their own use cases, their own implementation strategies, or their implementation stories. Something that's really interesting at this point is the Implied University, where it's at learn.implied.io, where we currently have 2 free courses. There's the Apache Druid Basics course, and then the more advanced ingestion and data modeling course. And for now, they're free, so take advantage of that and sign up and go through the courses. They're hands-on courses that I think that I like a lot. You learn a lot by doing things hands-on. With that, I'll leave you just with this. This is the final, my final slide, list of ways to contact us. There's our email, the community team email account. There's like I said, the user forum. There's meetups like this one, where we're looking for more meetup opportunities. So if you know of any others that you'd like us to participate in, we'll gladly do so. There's the Slack channel, the training program I mentioned, and LinkedIn has a Druid professionals group, and you'll see news about us in Twitter under Druid.io or Apache Druid tags. So with that, I'll say thank you and open it up for, if we have a little more time, we have about 4 minutes for any other questions. Yeah, looks like I answered all the questions. Let me see the chat. Going once.
Well, that's it. I think
I
that
guess
means
so.
we're super comprehensive, Sergio. Thanks again for delivering such a useful presentation, and you've also included all the ways that people can reach out to you. So if you're a little shy, or if you think about a question you have later on, please do not hesitate to reach out to Sergio, and the Implied community team is on the Druid Slack channel. So you can also find us there or on the Druid user forum. So thanks again to, I think we had about 30 folks join us today. We really appreciate the participation.
Thank you. Thanks, everyone.
Bye.